Good morning, everybody. First, I'd like to thank the organization AMAP for letting us come and present on this material and what we're doing with it. It's been an interesting ride for me. I actually moved from California out to Michigan. I still feel like I'm a little crazy for doing that. As you can see, the weather here is beautiful, and my wife sent me pictures of the snow today. So I'm still questioning my sanity. So what we've done is started this modification process with working through a normal type of study to evaluate how isocyanate-based chemistries will react within asphalt and within the asphalt structure. We started with performance grading and studying and looking at the UTI expansion, what kind of reaction would we get, what type of improvements overall on the performance grading of asphalt you could achieve through different levels of modification. Then we moved from there. We have actually laid down some paving trials out in the Midwest, as well as overseas. It's a global project that is also paved, so they paved in Germany. And then from there, we started doing some formulation studies. Let's see what kind of interactions we see when we add the other additives that we typically use within asphalt. Well, that didn't show up. There should be a map on there. What I wanted to introduce here to everybody is, as most of you know, BASF is huge. It's about 140,000 employees worldwide. What most of us here are used to is the people out of Charlotte. Those guys deal with your latex that you put in your emulsions. The group that is actually leading this project and this initiative is out of Wyandotte, Michigan. And with that move that I commented on earlier, I actually moved out and we built an asphalt lab and are starting to do research in that area as well out of that facility. So they're all over the U.S. You can see that we have the different states and everything listed, even though the picture didn't show up on there. So with that, with the background, what we did is we were trying to take this isocyanate, which is essentially it's a precursor to a polyurethane type chemistry, okay? It's used as a building block for all kinds of stuff that you would typically use in your day-to-day life, okay? We tried to fit that into the paradigm that we have in the asphalt industry of what type of modifiers it is. So this material is it's a reactive modifier. It is a chemical modifier. And this list is the one that AMAP has that they have out on their website. That's available for everyone. What we found is that when you use an isocyanate-based chemistry, it doesn't really fit very well into this. While it is a chemical modifier, it doesn't just increase the binder stiffness. It adds a whole lot of other functionality. So it doesn't really fit there as well. So we can call it a chemical modifier because essentially that is what it is. However, it adds a whole lot of other things to it. One of the things that this does, and I'll show you later in one of the slides, is it has a lot of potential in the interaction area with the different SBSs. You could kind of use it interchangeably with a lot of stuff to achieve the same type of modification. It's a liquid modifier, so you can simply inject it into your tank. It's low shear. You can mix and stir, essentially. In some of the trials, we actually were able to inject into a tank at the mix plant rather than modifying at a terminal, just for ease of use to prove out the operational feasibility of using this material. So from there, I wanted to talk about what type of modifiers we know and then what is an isocyanate, okay? We are working with some types of reactive polymers, terpolymers, copolymers. Some epoxies are reactive. We know PPA is reactive. In the asphalt industry, though, we typically say we blend it. It's blended and it's put in, and you have a blend rather than a reactive chemistry. What we found with this material is that you have to allow that time to react to achieve the full amount of properties that you want to achieve with it. So, and again, like I said earlier, we have found, and we were looking at how can we improve the binder properties. And then, is it equivalent or better or the same as our normal modifiers that we use? So within the industry, can I see a show of hands? Who has can't think of the name of it. Who's sitting on a cushion right now? Who's sitting on a cushion? I'm not seeing very many hands, and I'm a little bit worried about it, because if you're not sitting on a cushion, you're sitting on something different than everyone else, okay? The cushion that you're sitting on is likely made from this chemistry, okay? Day to day, you're using this material. When you get into a brand new car, the smell, that new car smell, it's related to this type of chemistry. Isocyanates are used for that type of stuff, okay? Again, you can see just from this list the amount of things that you're using every day. It's extremely flexible, meaning you could use it for a lot of different things. So that, again, the functionality of the different types of polyurethanes really just covers a lot of areas, a lot of functionality, from impact resistance all the way down to wear. So you can see with the different types of additives that we're currently using in the asphalt industry, such as rubbers, plastics. Of course, we're not really using metals. However, we can expand and utilize that functionality with a polyurethane type additive, or in this case, a precursor to the isocyanate-based chemistry. Okay. One thing I kind of want to show here, we have that resilience up there. And it's kind of a paradigm shift from what we're used to, right? We're used to looking at SBS as an elastic type material, but when we react in isocyanate, we can create anything from as hard as you saw on there previously to roller skate wheels, or you can be as soft as a super ball. Of course, this isn't the best place to bounce a ball. I could throw it at you guys and bounce it off somebody's head, but you can be stiff and flexible at the same time with the isocyanate chemistry. So again, with that paradigm shift, what happens, what are we normally looking at? We're normally looking at elastomers and plastomers. Isocyanate is an adhesive. If we go back to that slide that showed the different day-to-day uses, there's things on there like OSB board. It's used as a glue. Products like Gorilla Glue, they contain an isocyanate-based type chemistry. It's actually a liquid, as I stated earlier. One of the interesting things that we have found, and I'll show on slides coming up, is that the viscosity of the material once modified does not increase very much. But this also is a liquid storable at room temperature. It can be pumped straight into a tank. It's a reactive chemistry as opposed to a blend. So the fun part of a reactive chemistry is it then becomes part of that chemical compound or the asphalt binder, and it does not separate. Okay, we've ran up to 60 days of separation testing, held it in an oven to check it, and we had 0% separation. And again, it is a thermoset, and we are typically using thermoplastics. So in the industry, when I first heard thermoset, that kind of scared me. I didn't want to put it in asphalt. And again, what we have found is that we can use our typical methods of testing and find that you can just test it normally and get that improvement that we're looking for. So, what does it do? When you add this material, an isocyanate-based chemistry, to an asphalt, you are essentially bonding to an OH group within that asphalt on the asphaltene. And rather than building a structure that you normally see there with the physical mixing, where you have the asphaltenes and everything floating around and you kind of create a mix, we're actually bonding and stiffening the material through a chemical reaction, bonding those asphaltenes together. So, of course, that with that reaction, with that stiffening, we get some extreme rut resistance numbers, as well as a very low impact to your low temperature grading as well. So, I'd like to thank WRI for doing some research for us. JP and his group has been amazing. What we did as part of our study with TTI, you guys that may have seen Levier at Peterson last year, they presented some of the research on isocyanate-based chemistry, and I'm going to go through some of that here shortly. With that research, they selected 5 different binders at random. We kind of said we want a good binder and a bad binder, and we wanted to look at what the difference what would happen with an isocyanate-based modification. And then we took that and said, okay, well, what kind of reaction was that? Because we didn't know at the time. We sent it up to WRI and requested some research to be done and said, so these are the SBS, 3% SBS modified materials. Let's run some UV fluorescent microscopy and see what they look like. And then we took a 3% isocyanate-based modification and requested the same. And as you can see, this really just proves out my previous slide in saying that once it's chemically reacted, you can't see it anymore. It is gone within the structure of the asphalt. We have taken and run some FTIR studies and noted that you can react the material so it's no longer detectable on an FTIR. So, to the research that was presented last year at Peterson, we again submitted the material down to TTI, went down and conducted some training, asked them to blend this material and then run it through basic performance tests for performance grade and UTI expansion. So we could get a third party lab to verify the findings that BASF had found. Okay. The other task that was set to them was to determine the optimum dosage of isocyanate-based modifiers. So essentially we wanted to yield similar properties to SBS as much as could be done. So they took, again, the 5 different asphalts, some from the Midwest, some from down south, some from out west. We had a 0% control, then a 3% SBS, 3% isocyanate, and they just basically ran it through the normal slew of performance grade testing. As you can see on this slide here, it is a reaction-based chemistry. You can get an extreme improvement with the right type of asphalt. We were essentially able to take that 70 minus 22 all the way up to a 98, which would be a 94. Okay. In this case, we found that a lower percent isocyanate-based modification. I don't know if you guys can see the light blue colors there, that's the SBS modification. And get an increase at least equivalent or better than just using a straight SBS modification. We also took and looked at the low end, what happened to it with the different SBS and isocyanate. Again, we found that a lower dosage of an isocyanate-based modifier could yield equivalent or to a low temperature as an SBS type modification. It's very similar in effect when it comes to stiffening the material or moving your PG grade, with the exception of being reactive. So some asphalts will react much more. So again, with that, what we found was that UTI expansion on some asphalts of up to 114 degrees with just isocyanate modification. Okay, so comparing the two, and again, this was just comparing the everyday usage, right? SBS to isocyanate. And we found that with both, it could increase it equivalent to, or at least the same as SBS, okay? So from there, once we found that we could in a lab, modify asphalt, we could increase the UTI, we could increase the upper end. We said, well, let's go pave with it. So we went out in the Midwest. We did 2 separate paving trials. We paved 5 different roads. Over 12 miles of paving was done. And again, this was to establish operational feasibility. We also went out and hired a third-party testing lab. I'd like to thank Phil Blankenship and his lab for the work that they did. They were out there on the road, right off the paver, pulling, shoot, I don't remember how many boxes every few miles, probably upwards of, Phil's truck was full in the back. Twice, he just told me from the back there. And some of the things that we found, it's essentially just an anecdotal findings. You can see here with the modified asphalt, there was no sticking to the truck. They used a release agent once in the morning, and they never had to respray the back of that truck with any release agent. It was noted that it compacted easier than their regular necks. So we did have a control, and then our material, and then a control. So we basically capped the end of each road with the control, and then in the middle had the isocyanate-based material. So, again, part of our study was to prove out how it can be used from beginning to end. Our initial goal was to modify within a large asphalt terminal, which is still the goal. We are modifying the asphalt. But since it's a new material, most people, of course, don't want to put it in their tanks. I don't blame them. I wouldn't if you asked me either. So what we did find is there was some companies that were willing to let us modify in the MEX plant within some of their tanks there. So in each case, we modified 150 tons of liquid and allowed it to react, and then created the MEX and paved with it. And again, we wanted to check how it worked while paving. One of the other things that we did note that it seemed to not stick, well, it didn't stick to the bottom of a roller without the water on. We actually had to tell the guy to turn his water on so we would ensure that we didn't have any issues. So we've essentially proved out that we can modify in a terminal, even though we did it in the mix plant, because we were still doing it in the liquid tank at the mix plant. So again, it's been paved all over the globe, from Germany to here in the U.S. We also, in the U.S., whoops, there we go. So we paved in the first Midwest back in September, and then in October we paved another road in the Midwest, and this one was a neighborhood road rather than the rural roads that we did at the first trial. Both of those were 1.5-inch lifts. Actually, the total on the rural roads in the first Midwest trial was, it was 1.5-inch lift, and the total was a 4-inch on the Midwest with a 1.5-inch cap. And again, on the road in the Midwest, it was not a very long trial. On the second one, it was only half a mile long. Again, we pulled samples off of that, and again, submitted them back to Phil Blankenship for testing. I'll have some of those test results that he got off the first trial here shortly. And again, some of the anecdotal feedback that we've received is similar to what CJ was just saying, is a lower odor, and in this case it was actually a lower sulfur odor coming off the asphalt. In both trials, I was there actually, a really pretty face right up there would be me sitting on the back of that paver. The comments that were made to us from both companies was, hey, it smells less. Of course, both companies had no idea, so it's just one of those findings. So from that, we're actually launching a research project into say, well, why is that happening? In Germany, they noted that they can actually pave at a lower temperature. Based off of the test results, we get a lower viscosity when modifying with it. So because of that lower viscosity modification, it would only make sense that they could actually pave similar to a warm mix type material. Which of course gives out less emissions. You reduce temperature, you have less emissions. Pretty common sense, right? They did use up to 50% reclaimed asphalt in Germany as well. And then on the first Midwest paving trial, we actually had some RAP and RAS within the mix. and the workability was not reduced in any way. If anything, it was better. So, that being said, first thing I want to point out is just a little plug for Phil back there. If you look here right on this Hamburg wheel tracker, that's the Batman symbol. I don't know if you guys have talked to him, but it's Bat Lab, and he's the Batman. I'm not so sure about that. But. So what we did on this one, again, it had 12% RAP, 4% RAS in the mix. The control was a 3.4 on the Hamburg wheel tracker. Our blend was a 3.9 on the deformation, on the rutting. Statistically, that's essentially the same. This mix that they used is the one that they used for the DOT grade mix. There was essentially no improving this mix. What we need to do moving forward from this is find a terrible mix, and of course try to add this blend asphalt to it and see what happens at that point, see if we can actually get some sort of improvement. All laboratory tests indicate that we should see something better. So the other finding that we had from this trial as well was with Ideal CT, Phil took and tested that, and we were able to see just with this additive. So the additive loading on this trial was only 1%. So essentially what the customer was looking for at this point was, hey, can we take our 5828, just improve it to a 6428 and pave with it? So we just did it at a 1% loading level. Then we wanted to see what kind of cracking resistance we would get. And so the only difference between these two here is just that 1% isocyanate-based modifier. And you can see the average CT index went up significantly, just based off of those two things. The other interesting thing, and I'll talk about it shortly as well, is that when modifying with this, typically you use most modifiers and you'll bring your low end number up with your upper end when you're modifying. With the right asphalt, because it is reactive, you can expand from, well, you saw on that other one, the 114 UTI, it does not bump your low end up as much as it would normally with regular modifiers. So, the summary from those findings, again, so I've already spoke to the first two bullet points there, or 3 bullet points. So essentially what we proved, similar to what CJ said, actually I really enjoyed his presentation because he took some of my thunder. He said, it was normal paving, there was no difference. We paved with it, we rolled it, and it worked great. And in my mind, that's a win. If you could go out and add a new modifier, and then you could just normally pave with it without any changes to your laboratory or to your paving crew or to any of the stuff you're doing, you prove that you can do it, right? Again, there's little viscosity change when the binder is modified. There's no sticking with this material until it cools down. One thing interesting there that we have is Phil and I were walking along the mat. As it cooled down, you could walk on it normal, and then as it cooled down, I'm not sure what the temperature was, it started to get more tacky. So your foot would stick excessively compared to what it's normal. And so again, like I was saying earlier, it's an adhesive. So it's a glue. It's not just a elastomeric adhesive or an elastomeric glue. It's a hard glue. So, and then once it cooled off, it was, I mean, essentially like a rock. At one point during the second Midwest trial, we had finished with the paver had gone by. We'd done one roll with the roller, and somebody backed out of their driveway. And of course, you see the entire paving crew freeze. They're freaking out. They're going to have to go back and fix it. And as soon as they turned the wheel, everybody ran over to look at it, and there wasn't a mark on the pavement. It was very impressive. That material had a 2.75% loading of the isocyanate-based material. So from there, internally we took and wanted to look at, again, the interactions with SBS. What happens when we use it in conjunction, because with isocyanate-based material, you don't get the elastomeric properties that you do from SBS. You do get some, but not as much as we're looking for with a normal specification. Again, that's my point with the rubber ball. It's a different paradigm. So in conjunction with it, what could we do? Well, we can do some pretty extreme modifications with it. As you can see, this asphalt with just isocyanate did bump up that low end, but with a 3% loading, we were able to reach a 76 minus 16. It was a 76 minus 16 with an extremely low viscosity. Well, when we started using the different loadings of SBS, we got down to only a 3% SBS with a 2% isocyanate-based loading and have a 88 minus 22. At the same time, if you do it with a 2% SBS and a 3% isocyanate loading, it's also an 88 minus 22 with only a 1300 viscosity. Now, to touch on this a little bit, last week I decided to say, well, what's the extreme that I can take this? I don't have the data to share today because I didn't get it done in time. However, I did make a 94 minus 34 with a viscosity that was under 3,000. So the reduction in viscosity is amazing. Not really the reduction, but the lack of increase in viscosity. And again, that UTI increase is pretty amazing. And the other thing to note here is that with the SBS, we were able, in this asphalt, we were able to keep that minus 22. So from there, we also decided to run it against the massacre. And essentially, when you run them in conjunction with each other, and you can't see the white at all, you can get down to essentially a 0 JNR and 100% recovery. They work really great together, is what we're looking at. So, based off of these findings and off of these trials, this is our findings, essentially. And what we want to do, of course, moving from here is move on to other trials, do some more paving, try some different formulations, look at some different specifications, and see what else we can meet. Overall, it was extremely successful. And we were able to again, we were able to essentially pave exactly like you would normally pave, but have some extreme binder modifications. Again, I'd like to thank those that were helping us out, WRIJP, Planche, Michael Wardney, who did a lot of work for us as well, Texas A&M, the TTI, their group and their research they've done has been extremely beneficial. And then Blankenship Asphalt Tech and Training and all of his work that he's done with us as well. Any questions?
Anybody have any questions? I see, oh look, over here. I'm coming.
It's hard to see the
slowly.
light.
Now I can't see you. Right there?
Hello. I was wondering if you had any elastic recovery numbers with just the isocyanate as an additive.
I do. So again, like I said, you don't get much elastomeric properties. It's not an elastomer. It's more like my rubber ball here. If I throw this against the wall or something and you record it on a slow motion camera, you can see it smash and completely recover, right? However, it's not like a rubber band. You cut it, you damage it, it doesn't come back, okay? So you can get probably, I've seen a 10 to 15% recovery with it by itself.
What about with the SBS? Does that affect the elastic recovery when combined?
With the SBS, you can get extreme recovery.
Okay.
Yeah. So it's just in conjunction. Once you put them together, again, there's no reaction really that happens with SBS and the isocyanate-based chemistry. However, it's very complementary to each other.
Thank you.
Thanks, I see, yep, there we go.
Brian, I'm wondering if you had any idea of what the reaction time is from the introduction of the isocyanate with the asphalt and complementing with the SBS.
With asphalt and SBS at the same time, essentially, it depends on your loading. So a 1% modification can take an hour to 2 hours. Once you go up to 2%, it can take up to 6 hours. It just depends on, again, on that loading and, of course, your agitation.
I was curious to know the cost compared to SBS, like percentage-wise, if you're putting in 2% of both or 1% of both, how does it compare in cost?
Come see me later.
Anybody else? You're going to ask a question?
Don't make me throw the ball.
So, so when you add it, can you add it to just the neat asphalt and then add your polymer, or would you add it to the polymerized asphalt already and get the same properties?
You can add it either way.
Anybody else? All right, here we go. Thank you.